Thank you.
No problem. Good luck, guys.
Thanks. Good. All right, I'll get started here. So welcome everyone to our spring series of Vamos. This is now officially an APS series. Sorry for the delay here. We're transferring over the Zoom licenses, so this has made things a little bit more complicated as we get the stream going. So for our first talk today, it's a pleasure to welcome Dave Schuster from the University of Chicago. Dave is a pioneer in the use of superconducting circuits for quantum science, and this began early in his career. After completing his undergraduate degree at Brown, he pursued a PhD at Yale in the group of Rob Shilkoff, where he conducted some of the first experiments on super quantum electrodynamics. His work during this period really kicked off a technology which is now used by many labs around the world, not to mention also in private sector quantum computing efforts. After a postdoc at Yale and then a brief excursion into ions at MIT, Dave was snatched up by Chicago. Building on his earlier explorations in quantum optics and quantum information, Dave has used superconducting qubit technology to study things like multi-mode cavity QED, topological circuits, many-body physics and quantum simulation, random access quantum memories, optimal control techniques, and this list goes on. Dave has, of course, been recognized with numerous awards, a subset of which includes a Packard Prize, a William McMillan Prize, and an NSF Career Award. Finally, let me add that Dave is a super collaborative and fun guy to talk to, so I highly recommend joining for the post-Vamos discussion after his seminar. As a reminder, Dave will stop a few times during his talk to answer questions. These questions you can post in the Q&A in the Zoom or on YouTube in the, I think it's called the chat. It's the chat, right? It's like the chat thing. Yeah, okay. Yeah, with that, Dave, thanks for coming.
Great. Yeah, thank you for the great introduction and also for inviting me here to speak. Let's see. So people see the laser pointer. Good. Okay. Yeah. So today we're going to talk a little bit about some of the quantum simulation efforts that are going on in my lab jointly with John Simon. And so in the atomic physics community, there's been this long tradition of trying to build synthetic, condensed matter-like systems out of atoms. And today we're going to talk about kind of a similar sort of program, but instead of using ultra cold atoms, we're going to use microwave photons. And so we're going to start at the very beginning, like how do we get our photons and then build from there. And then I'm going to, and so that'll be kind of the first part of the talk. Then we'll talk about a way. So one thing that's different about photons compared with atoms is that if you have an atom, unless you drop it, at least it will stay there. Whereas a photon can just be absorbed. There's no conservation of mass or charge for photons. And so we'll try to understand how we can use sort of a unique capability of being able to really engineer the dissipation in these systems to actually turn decay from something which is a bad thing into something that actually helps us stabilize particular states. And then we'll take another thing, which also is one of the challenges of our system, which is that there's disorder, and we'll try to use the disorder to actually help us prepare many-body states. And then lastly, hopefully we'll have time, I'll talk about how we can actually realize a synthetic magnetic field for photons. A lot of the most interesting condensed matter phenomena happens in strong magnetic fields, like the fractional quantum Hall effect, for example. And it would be great if we could do that study that type of physics with photons. But of course, lasers don't bend in a magnetic field, so we need to think of a way to get that kind of an interaction. Okay, so. We're gonna work in a system which may be familiar to some of you in the atomic physics context, which is called the Bose-Hubbard lattice model. And so it's sort of a very basic model, but despite its simplicity, really you can, if you set up the lattice and the interactions right, you can pretty much get almost any phase of matter out of it. So it's a really generic kind of thing, and it's a good platform. And it turns out that, as I'll show you in a minute, the superconducting circuits just implement it very naturally. So it has a few components. I'll take you through them. So the first one is that each particle that you add into a particular site costs some energy. So the energy of a site is this energy epsilon times the number of particles or photons that you put in it. The next piece of it is this term, this J term. And what these operators mean basically is that I take the particle off of one site and I put it on the other site. And the rate at which something can hop back and forth is this rate J. And then the part of the interesting thing comes in, so this gives us like kinetic energy kind of physics. Then in order to get interactions, there's many ways of doing it, but one of the simplest ways is just a hardcore interaction. And what this just says is that if we put one photon on, it's going to cost us some energy. But if we put a second photon on, this n squared means that it will cost a different amount of energy. And this term is written such that the second photon will cost an energy which is different from the first one by u. Okay, and you can think of that as the interaction energy. And it could be positive or negative. And so if, and depending on the sort of the ratio of this J and U, you can get into different regimes. So you can end up in a superfluid. If the kinetic energy scale is larger than the U, you get sort of a delocalized system, which has phase coherence. And then if you're in the limit where the tunneling is much less than the interaction strength, then the particles will effectively repel and get and localize to one particle per site. And what's an interesting thing, which is relevant for our system, is that actually it doesn't matter whether the attraction is negative or positive or attractive or repulsive. Actually, either way, if the absolute value of U is bigger than J, you'll still end up in this insulating state. This is called a mod insulator. And then there's a kind of a phase diagram of these, which has to do with the sort of the tunneling to interaction strength and the filling. And so we're going to be operating kind of in this regime here. And in the first part of the talk, we'll talk about being fairly deep in this mod insulator regime. And then we're going to reduce our density to get into something more like a superfluid regime. Okay, so how do we build these? How do we now build this thing and realize this physics? So we're going to use two elements. The first element is just a harmonic oscillator, but we're going to do the electrical engineering version, which is the LC circuit. And so if we plot the effective potential in terms of the flux or the current or something in here, we'll get a harmonic oscillator potential. And the energy excitations I'd like you to think of as photons. These are our microwave photons. And we're going to operate around 5 gigahertz. And since it's harmonic, we expect them to be evenly spaced. And so this is great. And you can make lattices out of these types of objects, but they won't be interacting. But they can still be quite interesting, as we'll see when we talk about the chiral lattice later. We also use these for readout, as I'll show you in a minute. But in order to get interactions, we're going to need to use a nonlinear oscillator. And so we're going to replace this inductor with a Josephson junction. So physically, a Josephson junction is just two narrow aluminum wires with a very thin oxide barrier, such that Cooper pairs in the superconductor have to tunnel between them. So they can't just, they sort of have to hop from one to the other. You don't need to know a lot about that for this talk, but effectively you could just think of it as a nonlinear inductor. But it's very nonlinear, so that even one photon changes its inductance. And the potential is kind of softening. So that actually the first photon costs 5 gigahertz to add. The second photon only costs, say, 4.7. So the U is, in this case, around minus 300 megahertz. Again, the sign isn't so important. And there are somewhat more complicated circuits that can give you a positive U if that's what you want. This particular one is called the transmon qubit, and that's kind of the workhorse of superconducting qubits. It's the one that IBM and Google and everybody use. Okay, so some of you may be familiar with atomic cavity QED, and one of the things that I did as a graduate student, and which we are using today, is this idea of circuit quantum electrodynamics. So we implement a very similar model to an atom in an optical cavity. It's a qubit in a microwave cavity. And the model is a pretty simple one. You have a harmonic oscillator, so that's the red part. So that's represented by the cavity. And then you have a qubit, which is like a spin, although it doesn't have to be a pure spin. It can have more more levels. And then there's this interaction term. And this interaction term you can think of as, right, you take a photon out of the vacuum and then put it into the qubit and vice versa. And so what happens is that if you have, let's say, an excited atom, you put a photon into the cavity, it can bounce around for a while, but it's at exactly the right frequency to get reabsorbed by the atom. And this process will happen coherently until, until either the atom or the cavity decay into some other mode. And if it's resonant, if they're at the same energy, that's what will happen. If they're off resonant, then this can't happen because it doesn't satisfy energy conservation. But we can sort of take this term to second order in perturbation theory. So you basically square it and you get an A dagger A and a sigma Z. So you get a term that looks like this. And the way to think about this term is that, if anything that's proportional to A dagger A, right? So that's is like the cavity frequency. So now what we have is something that looks like a cavity frequency, but it's proportional to sigma Z. So this is a small shift in the cavity frequency, but it's qubit state dependent. And so we can use that to read out our qubit. So we can basically, so this is just a very raw plot of the transmission of a cavity. And what you see is that when the qubit is in the ground state, the peak is over at this frequency, but when it's in the excited state, it's at a different frequency. And so if we drive, let's say, at this frequency, if the qubit is in the ground state, we'll get a lot of transmission. And if it's in the excited state, we'll get very little. And so we can tell whether we're in the ground or excited. So that's how our readout is going to work. And what's cool is this is a quantum non-demolition event. It doesn't actually affect it doesn't change the qubit state. We can also interestingly do the opposite. So we can use we could have just as easily interpreted this term as saying, well, we have, so and the shift is 2 chi. We could have just as easily interpreted this as saying that the qubit frequency, the thing proportional to sigma Z, now has a factor that's proportional to the number of photons in the cavity. And so if we now, instead of doing cavity spectroscopy, we do spectroscopy on the qubit, we also see that there are shifted peaks, but now there are multiple ones for 0 photons in the cavity, 1 photon, 2 photons, 3 photons, 4 photons. So we can really very directly see the quantization of the electromagnetic field, and that these things really are photons. So that's the 0th of the thing. And this splitting is also 2 chi. And so this is how we're gonna read out all the data I will show you is read out using this method. And then at the end, I'll show you that we can actually use the qubit to measure electromagnetic fields. And then I don't know how many people in the audience are cavity QED people, but if you want to sort of characterize how good a cavity QED system is and put that all in one number, there's this number called the cooperativity, which is sort of the good interaction strength, is d squared over sort of the product of the decoherence rates. And if this is above 1, it kind of means you can do all this kind of fun stuff of doing these resolved readouts and whatnot. In superconducting cavity QED, we've really gotten very, very good at it. We're now above 1 billion, and roughly speaking, you can do the square root of this many operations. So if we can do more than 10,000 operations in principle. So that's one of the kind of technical bases of all this. So in terms of the ingredients, so I already mentioned that you need qubits. This is what an example of one looks like. It's and you can see that most of the object is actually fairly macroscopic, and that's one reason why we can get very large dipole moments in fast operations. And but at the center, there's this tiny little Josephson junction that's just a few hundred nanometers squared. And then these things operate at cell phone frequencies. Why do they operate at cell phone frequencies? Well, mainly because we can buy cell phone test equipment in order to control it. In fact, our newest thing is a FPGA-based board that was, I think, originally developed for cell phone base stations, but we've now actually shrunk this whole experiment onto essentially a big FPGA board. I'll show a picture at the end, maybe. But anyway, we do a lot of instead of lasers, we do a lot of microwave control. It's mostly in this 5 to 10 gigahertz range, which, if you think about in terms of temperature, is about 250 millikelvin to about half a Kelvin. And so we want to be much colder than that because we don't want to have any thermal photons around. And so we go into a Dill fridge that operates at about 10 millikelvin. And so we don't get as cold as a typical atomic physics experiment, but we can cool a lot more stuff. So we can cool many kilograms of stuff as long as it's kind of metal or gemstones. Then we can cool pretty much as you'd like. And when you see a picture of a quantum computer, you're really looking at a picture of one of these cryostats, which is really just the heat sink and fan of your CPU in some sense. Now the interesting stuff goes in these magnetic shields. Okay, so now let's look at the actual circuit. So inside that can, we've got our lattice. So this is a lattice of these superconducting qubits. So each of these little crosses is a qubit. Each one at the beginning, now it has a junction, but actually we split this junction into a loop. And we have on each qubit, there's also a magnetic flux bias line that can put a small magnetic field in this loop. And that will actually change the frequency of these qubits. And so unlike atoms, every qubit is sort of slightly different. And so in order to be able to tune out disorder, we want to be able to tune these qubits. So, the downside of them is that they're not all the same, but the upside is we can tune each one individually very easily. So then we want to be able to measure each one separately. And so we actually give each qubit its own readout resonator that we're going to read out in the fashion that I just explained. And then in order to do the stabilization, we're going to need two more elements, and it'll become apparent while they're there in a few minutes. We're going to have another cavity, which is a little more strongly coupled than the readout cavities. So essentially, it's lossier. And then we have, and then we're going to have this extra drive. And so we're going to somehow use the fact that this cavity is extra lossy to make this stuff extra stable. So that's kind of the idea of the first part of the talk. So how do we, so now we'd like to kind of characterize our system. So first we'd like to say, that epsilon, what is the energy to add a particle? So we do spectroscopy on the qubit, that's this red line, and we find that there's a spike right here. And so that's the energy to add one photon. But nothing else happens. It looks kind of almost like a harmonic oscillator. But now if we do, we can put a pi pulse, we can actually, put this on for the right amount of time, we can put exactly one photon in, and then we can do spectroscopy after that, and then we get this blue curve, and then we see there's another spike here, which is going from 1 to 2. And so this difference, just you can read it off, is just mu. And so this is that sort of 250, 300 megahertz number that I mentioned before. We can also measure the tunnel coupling. So what we do is we take two of these lattice sites and tune them together, and we put one photon in the two sites, and we just watch it go back and forth by looking at the population of this guy as a function of time. And when it's here, it'll be low, and when it's over here, it'll be high. And if we just look at this frequency, that frequency just gives us 2J. So we can just directly read that off. Another indirect way, but I think it's kind of neat, so I'll mention it, is that we can just do lattice spectroscopy. This is sort of the equivalent of, in the condensed matter world, of doing ARPIS, right? So you're kind of exciting the spectrum and measuring the density of states. In our case, though, we have so few sites and such high quality factors of all these lines that actually we can resolve not just the sort of the general shape of the density of states, which is like the cosine that you would expect from a kind of a simple type binding model, but actually you can also resolve each individual state, single particle state. So so we can directly measure the band structure, and then you can invert from this to also figure out the J's if you like. And then the other piece is, how long do these particles last? How long does a photon live before it just dissipates into the substrate? And we can measure that as a function of our kind of the tuning, and we can model this very well. And it's a very small amount of decoherence. It's a small rate. So so putting these all together, we get these energy scales. And I think for any kind of many body system, the real key is to be able to have enough dynamic range between these energy scales. So we have interactions up here. We have our kinetic energy scale here. So they're kind of similar, but there's a separation here. And then importantly, all of our decoherence scales, these are kind of things we don't want, are all way down, 2 orders of magnitude below that. And there's sort of the disorder we can't tune out, and the phasing is kind of at this level, and then the particle loss is even lower. So that's kind of the key. And so Now that we have our system, well, maybe it's a good point. I can pause briefly for if there's a question about the setup. Maybe this is a good time for any questions about that.
Hey, we could maybe one question. So to what extent are square root C errors the limitation on the kinds of errors that are seen in this kind of system?
I would say they're, right in this thing, the sort of cavity QED part is just used for readout. So it's actually not particularly important. It's just, it just needs to be high enough that we don't mess up our qubits and that we can do the readout. It's mostly actually kind of the coupling between the qubits that matters. And probably in this system, it's a little lower. And for the first experiment, it basically, as I'll show you, it matters very little. It's very robust. The second experiment's a little bit more sensitive to it. But it's still, I think I think we neither have the billion level for this experiment, nor do we need it.
Got it. Okay, sounds good. Maybe as more questions accumulate here, we can ask them at the end of this section, so you can keep going.
Sure, sounds good. Okay. All right. So then so for the Bose-Hubbard lattice. So now, okay. So here's a sort of a cartoon of this lattice. So we have this problem, which is, let's say that you're supposed to get some interesting state like a mod insulator or superfluid or something even more exotic. We can craft essentially any Hamiltonian you want. But actually, the ground state is always just going to be pretty trivial. It's just going to be no photons, right? Because it's cold and photons cost energy. And so if we want to see an interesting state and we'd like it to be stable, we need to somehow protect against that decay. And so what we're going to do is we're going to make a very special site. So for a moment, just imagine I have kind of a magic site. And that magic site always has a single photon in it. And if the photon leaves, it's immediately replenished. And once it's there, it's very happy and stable. Okay, so for a moment, let's just imagine we have this magic device, and I'll show you how we can actually make it in a bit. And now we couple that site to this lattice. What would we expect to happen? Well, these two sites are coupled, and they have some tunneling between them. So this particle can hop over here. But as soon as it hops over here, this is empty, and we said that this one wants to have one photon, so it would magically refill. And then, but now this guy, has no nearest neighbor, so he can hop over. But then this one, of course, is free again, and so these guys can go, and this one can hop in, and eventually this will just fill up. But once it's full, an interesting thing happens. So now let's say one of these particles wants to hop. So this our kind of filling site actually can't add a photon because it doesn't have the right amount of energy. In our case, because our U is negative, it actually has too much energy, but regardless, there's no site there. So by energy conservation, we can't add a particle. This coupling is too small is much smaller than U, so we just don't have enough width to get there. Similarly, you can say, but why don't we just rearrange these? Why don't we put this guy on top of this guy? But that also costs, this one also has too much energy for that. And so you're kind of blockaded. And so we think of, so to be in technical terms, this is kind of a many-body gap, right? Because rearranging the particles at fixed particle number has an energy gap. And this is would say that the system is incompressible, that there's a particle addition gap. And if we have these two properties, then we can just fill up like this always. And so this is exactly this n equals 1 mod insulator. And and if one of these particles decays, it'll just refill. So it's stable indefinitely. And so okay, so how do we make that magic site? And so that brings up this sort of the special qubit with this extra reservoir and stabilizing drive. So we can take our qubit and think of it as this sort of, we can just take the first two levels, or I guess first three levels. And now imagine that we add now this lossy resonator in here, and we align it such that the 2 to 1 transition is the same as this resonator frequency. And this resonator is very lossy. As soon as a photon gets in there, it just leaks out on off the chip. And now what we do is, so this is much lossier than this. And so what we do is we drive at half of this frequency, which is importantly not resonant with this one. So we can add basically a pair of photons or take away a pair of photons, but we can't add one photon. And so we do that. And but now what can happen is one photon can get lost as can hop over to here and then get lost almost immediately, leaving one photon left in this one photon state. So it will go here, and then, but now because that photon is gone, it can't go back up, and so it's stuck there. And this should look familiar to an atomic physicist because it's basically optical pumping. It's just kind of a cavity enhanced version of that. And we can plot that for a single site. And what we see is that you start out and everything's in the ground state, everything's here, and the excited state is here, and the second excited state is here. And we drive this process, and eventually we just end up almost exclusively in the first excited state. So that does what we want. But we can also look at the dynamics of the system as well. So like, how does that, I showed you that cartoon, but what's nice about our system is that we can see every individual, site in our lattice, and we can also measure with really good nanosecond time resolution. So what we're going to do is we're first going to stabilize the site, or we're going to start in the ground state, and we're going to turn on our stabilizer, and then we're going to see what happens. And this is sort of the dynamics. And so you see very much what you see in that cartoon, right? There's sort of a wave of particles entering the system. And by the time essentially that these particles can traverse the system twice, it's basically full. The last site is a little bit messed up by the stabilization scheme, but all these other ones are basically go up to close to one photon. And here's sort of a more quantitative look at the same data. So we have this, everything kind of relaxes, and you can do this indefinitely. As long as you keep the power on, it will stay in the state. And our average fidelity is around 90%, with the loss basically due to the fact that in this experiment that resonator wasn't quite cold. There was maybe a tenth of a photon there, and if there's thermal photons there, that can actually the process can be reversed to put a hole in there. So that's sort of what limits the fidelity. But we can also look at not just the dynamics of the filling, but we can say like, well, what happens if a particle is lost? So I give you this picture that if a particle is lost, that it should somehow get refilled. But we can actually do that experimentally and see what happens. So now what we do is we stabilize it, but with one particle missing, with one of the sites missing. We sort of leave it tuned up here. And then we turn off the stabilizer, and then we very suddenly put it into the lattice. And so this is like putting a hole into the lattice, kind of like what would happen if you had a relaxation event. And what you see is that hole, so this is essentially propagating ballistically through the system. It may look like it's getting dissipated. This is actually not dissipation or loss. It's actually the fact that because you have a cosine dispersion relation in this, actually just the wave packet is actually not all moving together, but it's actually kind of spreading out a little bit. So even in simulations with no loss, you would still see this. But you basically have like a quantum random walk until, and it will bounce around many times. Now we do the same thing, but we leave the stabilizer on the whole time. And now what you see is that it goes, but as soon as it gets to the end, it basically gets absorbed. It's not perfectly matched to this, so it does reflect off sometimes, and then it will kind of get absorbed on the next round. And so we can really just watch these dynamics as the thing is stabilized. So maybe, yeah, so we've made this kind of mod insulator and shown how we can stabilize states, but only in the case of a kind of a gapped kind of phase. So maybe this is a good point to answer questions about that part of the talk, and then I can tell you about how we can do stuff which maybe doesn't have a gap.
Sounds good. So the first question here is, if you wanted to engineer a more complex geometry or dimensionality, how much flexibility do you have to do that with this kind of setup, this kind of scheme?
Yeah, I think there's a fair, that's a great question. There's a fair bit of complexity of possibilities. So you can definitely do 2D. And Will Oliver's group at MIT has a 2D lattice. And some of the companies which have effectively 2D lattices have done similar kinds of quantum simulation experiments there. You can see in this one is also a 2D lattice. So that's pretty straightforward. I mean, a thing that you can do, which is really unique to circuits, is that not only can you do 2D, or I guess plausibly one could do 3D, but because you can have wires, you can have like strange connectivities, or non-trivial long distance connectivities as well. So you can make even more interested things that would be very hard to realize in natural materials. Actually, Andrew Houck's group at Princeton has also done some interesting things where they make things in like hyperbolic geometries and things like that. So you can actually have a lot of freedom with circuits because you're not constrained to simple lattices. But yeah.
Cool. And then can you say again once more what limits the mod insulator fidelity, like the 90% single particle filling?
Yeah, so I mean, I think it was, at least in this case, it was a technical limitation, which is basically when this resonator, we had there was a small thermal photon population, just like due to inadequate filtering to some extent. To some extent, it's just actually kind of hard to get the photons really truly cold. But I think this one was a little worse than some of our other ones. And so there was probably about 1/10 of a photon in this resonator. And basically thermal photons in this reservoir become holes in the lattice.
Got it. And then one more question is, how do you prepare just a hole on the end?
Yeah, so what we did was we did the stabilization to prepare all the other sites, but then the last site, we just detuned from the lattice by far enough that it didn't that it sort of by many J's, so it didn't interact with the rest of the lattice. So we kind of then this was prepared in that all one state, and then this one was just empty because it wasn't talking to it. And then we would very suddenly sweep it into this lattice where it could then interact. And in the next part of the talk, we're going to spend more time thinking about that. We'll start with all of the qubits disordered, and then we'll talk about doing both like adiabatic and sudden kind of rearrangements to produce different types of states.
Cool. Okay, I think those are all the questions for now. So maybe let's keep going. And yeah, that sounds like a segue. Yeah.
Okay, perfect. So yeah, so I said we had this tunability, but and we use it sort of before just to statically tune out. So we maybe start like this, and then we would tune out so that we made a lattice where all the sites were the same. And we just sort of did that statically. But now what we're going to do is we'll start out intentionally with everything spread, and this stagger is picked specifically so that each one of these is sort of unique and controllable. And then we will dynamically tune them in and out of this lattice. And the idea is that if we want to prepare states with, let's say, a fixed photon number, but maybe not, let's say, just all of them filled or right up to this gap, then what we can do is we can excite individually these qubits or prepare whatever state we would like, and then we can adiabatically tune in. And so this is like when we're in this kind of initial state, our qubits are all separated. But this adiabatic theorem says that if we slowly change the parameters of our Hamiltonian, in this case the detuning, that sort of the ordering of the levels will stay the same. So if we excite the highest qubit, like qubit 5, we should end up over here, for example. And so so that's what we're going to do. We're basically going to put some number of photons in appropriate qubits, and then we're going to adiabatically sweep in here and then see what kind of a state we get when they're all degenerate. And so kind of the typical thing is, we excite, we're going to ramp into the lattice, and then to read out, we can suddenly pull them back and then measure. So let's do that. We have so first, before we do that, what we're going to do is we want to see like, well, how how fast or slow do we have to do this to be adiabatic or sudden? And so what we do is we have a ramp that goes up and then comes back, and it takes some amount of time. So if we do it in like 10 nanoseconds or something really fast, then it's so fast that we've basically gone in and out, and there just wasn't any time for the lattice to interact. Basically, if this time is much faster than 1/2J, then we don't expect anything to happen. If we go slow, though, it should actually kind of go in and then come back out, and then come back to where it was again. And if we go somewhere in the middle, though, it will actually kind of spread out within the lattice and then come back. So that's kind of this Landau-Zener crossing. And so we're going to kind of take advantage of this. So when we want to keep the state frozen, either when we put something in like we did before, or when we want to measure, we'll do things really fast. And if we want to go slow, and now we know how slow. I should say, I didn't include it here, but if you keep going slower and slower, eventually what will happen is just the photons will decay. So there's sort of a time limit here. If we go for, so this is like a microsecond. If we go for much more than, let's say, 10 microseconds, we'll have a very significant amount of decay. So this type of preparation, unlike the other one where you could just, as long as the power stays on it, it will stay in the state. This one you sort of have to do relatively quickly. Okay, so we can do this either suddenly or reversibly. And now let's see if we can actually make a state. So we're going to start by making a single particle state. So we'll put a single photon in Q5 here, and then what we're going to do is slowly go to a different, each point here is a different amount of tuning until we get to exactly the lattice state. And what you see is when we get there, we have actually the part, the sort of cosine like potential that you would expect for a particle in a box. And so these bars here are measurements of the qubit probability. So we go in, and then we very suddenly go back to freeze in those dynamic to the state of all the qubits, and then we measure. And we can just see the probability distribution of a sort of a k=1 state. And we can do that for actually all of the different states. So we have the so now the red bars are the data, and then the gray is the theory. And you can see we can do kind of the lowest energy, which is sort of like a cosine potential. The k=1, which has a single node, 2, which has 2 nodes, and 3, and so forth. So we can make all of the possible kind of single particle wave functions. So I mean, actually, an interesting question here is like when we do this, like you can ask like, is this do you think are we making an entangled state here? So we're basically putting a single photon in a box, and an interesting question is like, is this state entangled at all? And so maybe like I won't do like a poll or anything because we're already a little behind on technical reasons, but I'd encourage each participant to think to themselves, like, when we make this state here, is this an entangled state or not? Okay, and so come up with an answer to yourself, and we'll discuss it later. Okay, so we can also do this. It gets more interesting when you do more particles. So we can actually that was the single particle manifold. This is the 3 particle manifold. So you can see it's already getting to be quite a zoo of things. So this is only 7 sites. So I think one thing I found in this project is that you don't need very many sites or particles in order to really start to see many body stuff, and it very quickly gets to be where you can't keep track of everything microscopically. But I think this intermediate regime is kind of interesting because we can sort of really see this crossover between full microscopic control over the states to things where you sort of label like sets of states as particular phases. So what we did is we prepare each of the odd qubits. We put a photon in, and then we sweep them in, and then we get this kind of sort of very tiny superfluid-like state. And so you can kind of so we start here, and then we end up here, and we can just get the theory from just exact diagonalization still, and we see it's a pretty good agreement for what you would expect sort of a 3-particle superfluid state to look like. we can also kind of, again, it's already getting messy. And so, at this point, we can still numerically diagonalize, but you'd like to sort of connect this to sort of a Hamiltonian that is and description that is good in the thermodynamic limit. And so this is really a very good example of like a Tonks-Girardeau gas of impenetrable bosons. And so there's you can kind of describe this as basically a many-body wave function, which essentially looks like particle in a box states times this factor, which basically accounts for the hardcore boson nature. So you can immediately see that, if the wave function has a node anywhere where another particle is sitting. So you can kind of think of it like that. And so these are the points are this analytic theory, and the bars are now numerical diagonalization of our system. And you can see they don't agree exactly, but they're actually certainly qualitatively a pretty good match. Okay, so now I want to come back to this question of entanglement. So when we do, so what we're going to do now is we are going to do the same type of an experiment with different numbers of particles, with a single photon, with 2 photons, and with 3 photons, and we're going to put them into the lattice, and then bring them back. And we're going to vary like how close to the lattice we get. So here's like we didn't move them at all. Here's they go all the way into the lattice and before coming out. And what we'd like is just one number that measures the entanglement. And this is not a unique choice, but one way you can, the basic way you measure entanglement is you take one section of the system and you measure it a bunch of times separately from the rest of the system. So the rest of the system, you're kind of averaging over. So mathematically, that's taking a partial trace of the system. And basically, if what we make is a pure state, but if it's entangled, when we pull this out and measure it separately, it will look mixed because it's entangled with this. So that's kind of the idea of all of the entanglement measures. And so this one basically has this is kind of a normalized version of this, where we basically take the average of the purity, which is this trace rho squared of the different sites, and it has the property that if there's no entanglement, it should be 0. If there's if there's kind of maximal entanglement, this would be 1. So this is really easy to check for like a Bell state or something like that. It's maybe not so obvious for a mini particle state, but it's a reasonable metric. And so what you see is that when we actually go all the way into the lattice, that we do see that there's significant entanglement. And then before I said would you expect there to be entanglement for a single particle? And many of you, I imagine, may have said, well, I mean, how can there be entanglement if you have a single particle? I mean, there's one photon, it's a particle in a box, it's a wave function. I did that as an undergraduate in quantum 1, that I didn't even know about entanglement then. There can't be entanglement. Other people may have said, well, especially qubit people would have said, well, there's 7 qubits and they're interacting, so there clearly is entanglement. And I think this sort of gets at the nature of entanglement, which is that it's fundamentally about what basis you're in, right? So I think neither of you would be wrong in some sense. I think it's perfectly reasonable to say that, well, it's a single particle state, and therefore it shouldn't be entangled, and that's certainly true on that basis. And that's why we don't usually think of metals, just normal metals, as being entangled. But on the other hand, if you look at things from the perspective of sites rather than from the perspective of quasi-particles, then then the system is very highly entangled, and even for a single particle. And the same thing is true for a metal, incidentally, right? And so there is entanglement when you have a single particle. And you can think of this actually in qubit language. This is it's a well understood state. It's called it's a W state or Dickey state, and it's certainly an entangled state. And as you put more photons in, you have more entanglement, with the most being at half filling, which is in our case about 3 out of 7. And we should also check what happens. You may have noticed here that it didn't go all the way back to 0. And that's because there's another thing that the qubits can be entangled with, which is the environment. And so, this experiment takes some time. And so if we just, if we do this reversibly, so we're still going into the lattice and back, but we've already shown that if we do this at the same speed, then it should just come back. So it's not that we just, somehow the state is getting destroyed when we move in. We can actually, it's still a pure state when it's in there because we can reverse it. And then, but it's not perfectly reversible because it does take time, and we do lose some, some of the photons. And so that's what sort of sets this baseline here. Okay, yeah. So we actually did some really interesting things on correlations as well, but I'm worried I won't have time. So maybe we'll save that for later. But I can take any questions on that section now.
Cool, sounds good. So one question is, in what sense are these states superfluid? Is there a way to measure the coherence or the phase?
Yeah, I mean, so if you look at these, basically you can kind of see that there's sort of an oscillating probability and phase that sort of mimics the single particle state. So it's not, it's not exactly that, the system is so small, and there's open boundary conditions. So it's not that you can't quite say that like the 3-particle state is just like the k equals 3, wave function, with n particles in it. So you can't quite do the thing that you would do with like a BEC, just because of the system is so small and has boundary conditions. But you can kind of see you can see sort of the right periodicity and such. And you can, and of course, I mean, numerically you can evaluate any of the properties you like, but I would say you kind of see it in the sense that you do see the momentum that you would expect, and you also, well, I mean, you can see correlations, although that's more from mostly from the interactions in this case.
So another question is, how do you achieve tuning of the qubit frequencies within 1 nanosecond? Is that achieved by using an off-resonant flux pulse? Is there any flux trapped in the sample due to this fast change of flux?
Yeah, so these lines that you can see here, we just put a small current, and that puts a magnetic field here, and that effectively sort of tunes the energy scale of the Josephson junction. And the only limit to that speed is whatever the microwave engineering is, and roughly speaking the Josephson frequency, which is like 15 gigahertz. So you can do it in of order a nanosecond or so. We have filters, so we probably it's more like 10 for us. But and then the other question was about vortices. So we do try very hard to avoid vortices. So we have several layers of magnetic shielding, and this is a small current. So it's only it's a niobium ground plane, and it's only a few milligauss of current that's fairly localized. So we don't expect that should nucleate any vortices. But if we do bad things like put too much current in, then we can get hysteresis, which would be due to creating vortices. But if we're operating in sufficiently gently, which we try to do, then we don't have that issue.
Cool. Another question here is, what is the time scale of your adiabatic sequence and also the Ramsey coherence time of the qubits?
Yeah, great question. So let's see if I've got a good, so this is sort of probably the best slide for that. So so you can see the fastest we can go is like 10 nanoseconds or so. And then, we're pretty well into this adiabatic regime, in around a microsecond or a couple. So usually we're, we say between 1 and 5 microseconds for adiabatic stuff, and then maybe like 10 to 100 nanoseconds I guess so, maybe a few nanoseconds for the adiabatic, for the fast stuff.
Got it. And then maybe one more question. This one's from me. So the scheme for measuring global entanglement here is basically you're looking at, these are all single site statistics, right? So you're like using the fact that photons are conserved to get the reduced density matrix.
So we're just so basically, in some sense, you have it in, then you pluck one of the qubits out, and then you measure, you measure its purity. So you just measure like its density, and then
I see. And then tomography on just one qubit when you do this.
Yeah, exactly. And then we do it for qubit 0, and then we do it for qubit 1, and then we do it for qubit 2.
I see. And the fact that you're in this hardcore limit means you're never going to have more than one excitation. So it's like really just tomography on a spin 1/2 system, basically.
Yeah. Yeah.
Can you do, I mean, if you can tune the couplings between the qubits, presumably you could also do tomography on a 2-qubit subspace or a 3-qubit subspace and so on, but maybe that's just too time intensive.
Yeah, so one thing we've developed, and actually I did have some slides, but I just was worried about time. So we have, which is, we've got, we can do, in principle, we can measure all of these simultaneously. And right now, kind of for technical reasons, we can do kind of 2 at a time. And so we can also measure directly correlators. So we can measure like G2 functions, and we can measure kind of those things and other kinds of correlators to see if, just to show that, for example, that you don't have 2 photons per site, but also that, you kind of expect, for example, that you would be anti-correlated on the site itself, but you can also see that you have a suppressed occupation on nearest neighbor sites, and even depending on how many particles you have, there's a different length scale for how for that fall off, so you can measure that using the correlations, and you can also, we can also, in principle, if we measure the phase between 2 qubits, we can also kind of try to measure phase coherence between qubits to sort of maybe more directly measure the superfluid question that was asked earlier.
Good. All right. So maybe we should keep going here. And, if we run out of time, Dave, I think we can save questions for the post-Vamos discussion.
Sure. Okay. So yeah, so the last piece is a little bit different. So now the lattice we're going to be talking about is totally a linear lattice, but we're going to try to create an effective magnetic field, and we'll have 1 qubit, and we'll use that as kind of our like probing, to be able to put photons in and take photons out and interrogate it. Okay, so first, like, what is a magnetic field? So one of the fun things about doing this project is it sort of made me really kind of think hard about what is a magnetic field. And so I think the essence of the magnetic field is contained in this Aharonov-Bohm effect. So if you have an electron and it traverses a magnetic flux, even if it actually is never in the magnetic flux, right, it accumulates a phase. So if it goes this way versus this way, there'll be an interference. And and this is the thing that shows up in the Hamiltonian. And I would say, in essence, this is the thing that we care about. So so not only does this happen whenever you have a magnetic field, but if you can engineer this effect, then you've effectively, all the behavior of your particles will be like the behavior of charged particles in a magnetic field. And including things like getting cyclotron orbits in bulk, and then having kind of these skipping orbits. So that basically the essence of the quantum Hall effect, and with topological protection from backscattering on the edges, and flat levels in bulk, and all the and protected edge states, like all the things you would associate with quantum Hall physics, you will get if you can engineer an effective Aharonov-Bohm effect. And so the way that we do that is we're just going to create a square lattice, but every 4th site we're going to try to make it non-reciprocal. We're going to make it chiral so that you get a phase which is different going this way than going that way. And so if we can do that, I claim that we'll be able to get all this physics. So I'll show you how we can engineer these sites, and then we'll actually do measurements where we can actually see this physics directly. Okay, so for our sites, we're going to use LC circuits, but we're going to do this in 3D. So it's a niobium cavity that looks like this. So you can think of that little post as being a quarter wave resonator, and then for our tunnel coupling, what we're going to do is take 2 of these guys, and we're going to drill a hole from the back, and then we get something like this. And then our chiral site, we need something that breaks time reversal symmetry, and so we're going to use what's called a YIG sphere, a yttrium iron garnet sphere, which is a ferrite. It's sort of a ferromagnetic insulator, which is biased with the magnetic field. And you should just think of this conceptually. I like to think of this as just one huge classical macroscopic spin, and I'll show you how that gives us the properties we need. And then we're going to put a qubit in there at the corner, and we're going to use that to sort of be able to do cavity QED on the system. And so this is what the system looks like. There's sort of a little black ball in each of these sites that has the gig. So these are the kind of the single post sites. These are these chiral sites, and then here's where the qubit would go. So let me explain this chiral site briefly. So this is what it looks like, and we have a magnetic field here. And so you should think of this black sphere as a big spin, and it has a certain sense of precession. So it might be, so let's say, going around like this. And so and now we have these three posts. So there's one mode which is just a quarter wave mode with three posts all kind of in phase with each other, and that's this green mode, and that doesn't do anything particularly special. But then there's a degenerate set of modes between these guys, which you can think of as like, if you think of this, this one's like an S-like mode, and there's like a P-like mode, which is like PX and PY of these. And you can these are degenerate, so you could diagonalize them with like linear polarization or circular polarization. But if we think about it in the circular polarization, so this is one way. Imagine that the spin is also precessing this way. So if you kind of stare at the middle and try not to look at the post, but try and look only at the center, you'll see that basically the arrow is just spinning around anti-clockwise. And so if the spin is precessing in the same direction, they're co-rotating, and they're gonna have strong interactions. And so you'll get a bright mode, which is very strongly split. But the other mode of the cavity is precessing clockwise, and it's counter-rotating with respect to the spin. And so that one is basically going to have almost no interaction, and that mode will be dark. So that's this blue mode. There's some inhomogeneous broadening. So ideally you would have just this red big avoided crossing from the bright mode, and then a blue one that just has no crossing at all. In practice, the field isn't perfectly homogeneous, either the bias nor the RF field, and so you get some higher order modes. That's what's shown here. But for example, if we go down to here, let's say, what you can see is that the bright mode is pushed separately from the dark mode, and so that means that now energetically this thing wants to be circularly polarized. So and you might think, well, you want this thing to be chiral, so you put your chiral spin thing in there, and so clearly you want the mode that talks to that strongly to be the mode that you use. And the bright mode certainly is chiral. So the color code here is like the non-reciprocal phase. So you see, so this mode is reciprocal, it's got 0, but this mode certainly is non-reciprocal. But actually the dark mode is also non-reciprocal. It's just the other mode, it's just as non-reciprocal as that. And we like the dark mode even better to use for our physics, because you can see it doesn't really care about the magnetic field, and there's essentially no participation of this yig, which might be a little lossier in this mode. So we like this one, and we just operate down here where the superconductor, where the field isn't too big for the superconductor, because magnetic fields and superconductors don't love each other so much. And then, but we still have a very big sort of time reversal breaking gap. And so we're going to basically build our lattice at this frequency and hope that this one is sufficiently far out of the picture that we really see just stuff in here. So we do that. So if you can calculate what the band structure should be for something like this, for kind of an infinite strip of the stuff, and you get this type of a band structure, and you can sort of see that you get sort of flattened bands here, and you get and these have different Chern numbers, and you get edge modes that come down and connect them. And this energy scale, we picked the hopping to be about 50 megahertz or so. So we get so it's much smaller than that other time reversal breaking gap, so that we can sort of all be in this dark manifold. And so we can now do spectroscopy on it. So if we just sort of probe at one of these sites, and so this one is we probe like on a bulk site, and we see what we see, and what you can see is that there's a bunch of peaks, and that the ones like the green ones are the bigger ones where we're in the bulk. It's a very small sample, so these wave functions have a little bit of participation everywhere. And then if we probe one of the edge sites, then we actually see the modes, these red and blue modes, stuff in the gaps, but we don't see too much in the bulk. And so that's already kind of some evidence that we really have edge states and bulk states. But what's nice about this is a macroscopic object. yeah, if I maybe afterwards I have one on my desk. I can show it to you. But this is like an inch. So we actually just put a connector on each one of these sites, and we can measure them individually. So we can do microscopy in some sense. And again, we have both. We can measure it with single site resolution and also very fast time resolution. So we can actually just make a movie of this thing. Well, first we can just make an image. And like you can think of this as like an equivalent of an STM image. So if we excite here and then we just look at the participation, the sort of population here, we can see that this one really is mostly occupied on the edge and not so much in the center. If we drive this bulk mode, we see that we get sort of a localized excitation here, which doesn't have too much on the edge. And so this gives us spatial resolution, but we can also do it with time resolution. So we can actually do this as a function of delay, and then we can make a movie like this, and you can see it going around, and you can even see it kind of avoiding some of the backscatter. And it's clearly going around in a chiral fashion and not going around, it's not just sort of spreading out over the whole thing. We can make that more quantitative by by just sort of taking a slice, and we can measure the decay time. And I think this is a pretty unique system from synthetic kind of magnetic fields, in the sense that I think it's really the only one in which you actually can go all the way around the whole system many times. And most other ones, they're linear, and so you still get a curve like this, but you're getting the 1/e like distance in terms of sites is like usually like 1 or 2, and in this case, you can sort of see we're getting hundreds of sites. You can also measure like the dispersion and the velocity of the wave that way. And so then what we'd like to do is actually put a qubit on there and see if we can actually do quantum manipulation of these modes. And so there's sort of this trick that you can do where if you drive the qubit kind of at this particular, at the frequency between sort of the second excited state of the qubit and the lattice frequency, you basically can induce a kind of a I like to call it a stimulated vacuum Rabi oscillation, kind of stimulated version of the process I showed you at the very beginning, where you can add exactly 1 photon to the lattice or take exactly 1 photon away from the lattice. And then that has this kind of, when you're on resonance, you see this kind of a characteristic chevron-like oscillation. And so if we do that for all the individual modes, we can now sort of see the spectrum of it again, but now what we're actually doing is, instead of just seeing kind of peaks, you can see actual individual photons moving in and out of these individual modes. So these are sort of like different momentum states or different edge states or bulk states inside the system, and we can address each one individually and put photons in. And in a case like this, where you have like, or this, where you have like, you were driving so strongly that there's sort of hybridization of these two modes, it's actually like launching sort of a well-resolved wave packet. So if you take a slice here, you can actually see kind of that single photon going in and out and eventually decaying. And we can also, if we put some photons in the cavity, we can use the qubit as a photon counter and measure sort of the amount of occupation as a function of power that we put in, and just count the amount of photons. So we have full control of the system, and what would be next would be to try to put in, if we put a qubit on every site, then we've done numerics that suggest that there should be a Laughlin state that we could stabilize using the first scheme that I talked about. So with that, I'll kind of start to conclude the talk, but I just wanted to mention some other efforts in our lab. We do a lot of stuff. So that was what I talked about, our quantum simulation efforts, but we try to make new qubits. We also use sort of this qubit technology and this photon detection technology to help accelerate dark matter searches. We do a lot of stuff on instrumentation. So we're actually building qubit controllers in collaboration with Fermilab that actually can take that whole rack of electronics that costs hundreds of thousands of dollars and put it on a single board that costs less than $20,000 and can control more stuff and do all kinds of fun real-time things. We do kind of hybrid systems, so we're studying electrons on superfluid helium, and we're working with John Simon on Rydberg, trying to do Rydberg cavity QED with millimeter wave superconducting cavities and sort of just millimeter wave circuits and error correction schemes and other fun projects as well. And I'd like to thank the people who actually did the work. So that's so Brendan and Alex did kind of the first experiment that I mentioned, and then and then they were joined by Gabrielle and Andre. So Alex is now a professor at Purdue. Andre and Gabrielle have joined, and the three of these guys did the adiabatic preparation. And then Clay and Alex and Meg have done this synthetic magnetic field work, and all of this was a joint work with John Simon. So with that, I'll just throw up the conclusions, and I'm happy to take any questions and just hang out for the after session.
So much, Dave.